All right, I'm George Merza, and I'm going to go through the second part of the final assessment. And to start off this problem, I'm just going to write down the energy rate equation because that is essentially what drives this entire problem. Now, due to the fact that this problem has multiple given pieces of its state, we know that it is steady state, so that means that the E rate is going to be equal to 0. Kinetic energy and potential energy can both be neglected, as well as any stray heat transfer, so that means that the Q rate, the potential energy and kinetic energy components of the energy rate equation all become 0, and you are left with the rate of work on the left side, which equals the mass rate times the entropy in minus the entropy out. Now I'm going to go ahead and write down the givens in order to just get it out of the way so that I can begin solving for those entropies and then eventually that mass rate. Okay, these are the givens, and since we were told that the gas can be treated as an ideal, the air can be treated as an ideal gas, we can just use the steam tables for ideal gas and find the H values, which in this case, one of them are very simple because it falls at 310 Kelvin, which is directly given on the graphs, and that's just going to be 310.24 kilojoules per kilogram. The other one I have to interpolate. All right, so after solving for that value, we now know that we have everything that we need for the final answer, because the work rate done is given to us as 1.9 kilowatts done to the system, so that's going to be put in as a negative, which means that it's positive on the right side. Once I move it to the left, it'll be a negative 1.9 kilowatts. And that is equal to the mass rate times 288.15 minus 310.24, and that is given in kilojoules per kilogram. And then I just have to divide that value over. And this is the final answer. It ends up being in kilograms per second, which makes sense because it's just kilowatts divided by kilojoules times kilogram. So kilograms end up on top. The kilojoules per second of kilowatts, the kilojoules end up just getting canceled out by the kilojoules of the kilojoules per kilogram. So, yeah, the final answer is the mass flow rate needed to accommodate these given variables is 0.086 kilograms per second.